So let's take the basic example of a simple pendulum, or we can call it as also one link manipulator, because it can be, it can also be used without gravity, so where it doesn't really become a free fall pendulum. So we'll see how we can basically derive its equations of motion. Let's take the pendulum like this. So this is our coordinate axis, and let's assume this is the joint, and this is the length of the pendulum, or the one link. This defines our x-axis, and this defines our y-axis, which is our, as per convention, we can say this is x naught and y naught. So some basic assumptions. We'll define that the link has some mass m, and it has length L, and it is hinged at point O. All right. So the first step is to actually put up the coordinate axis. Again, the frames that we basically do in robotics. So in this case, we can attach another frame on this link, which could be something like this. So along the axis of the joint, that is this one, out of the paper or out of the board, it will be Z1, and this can be taken as X1, and this will act as completing the right hand. As per the right hand convention, this will be Y1. All right, so which in turn would make this define this as theta, or you can say theta 1 in this case. All right, so we'll derive the equation of motion using the Euler-Lagrange, or you can say Lagrange method, or the energy method. So in that case, we know that we need to find out the function L, which is the Lagrangian, which is nothing but the kinetic energy, total kinetic energy of the system minus total potential energy of the system. And the equation of motion is given by d by dt of dou L by dou theta dot minus dou L by dou theta is equal to the torque. All right, so we are supposed to get something like this: m theta double dot plus h plus gamma is equal to tau, which is actually the equation of motion in a kind of a state space form. All right, so in order to find out L first, so we need T and U. T is the kinetic energy and U is the potential energy of the system. So since this is one link system, so apparently it is very easy. So we can define, let's say first, maybe in an easier form, we can first find out the potential energy, that is U. So U for this link is nothing but mgh. So m is the mass, g is the acceleration due to gravity, and the height, actually, if we take this as a lumped system, so we can consider the mass to be concentrated at the center of mass, and let's assume this is a uniformly distributed kind of a link, a homogeneous link. So we can assume the center of mass to be at the center of the link, which is L by 2, because L is the total length. So we can consider that mg L by 2, but L by 2 is the length of the link. We have to consider the height from the ground. So if this is the point of center of mass, if this is the center of mass, so this is the height that we're actually interested in, that is this one, and L by 2 is this. So it will be L by 2 cos theta and L by 2 sin theta. So this will be L by 2 sin theta, because cos theta will be the base component, sin theta will be the height. So we are interested in the potential energy, which actually is proportional to the height from the ground. So it will be mg L by 2 sine of theta. All right, so we can also we can also write it like this: mgl sine theta. We write as sine theta 1 divided by 2. All right, so this is the potential energy of the system. Now, kinetic energy of the system is given by the kinetic energy due to linear velocity plus the kinetic energy due to angular velocity. So it's half of I omega square. All right. For this system, we need to find out, which means we need to find out what is V and what is omega. So omega is very simple. Omega is nothing but theta dot, which is the angular velocity. If it moves by theta dot as the angular velocity, so that would be the omega for it, and obviously it will have a direction, that is the z component. That is, we can also write it as E1 cap. So this defines the omega vector. We can maybe put it in this form also, arrow form, or sometimes we put it in bold form, which represents the vector, that omega is a vector. Fine. So this will be, even if we transform this to base frame x naught, so this will, because E1 and E naught, that is z1 and z naught are same, so there will be no change. So we can also write it as theta dot, or even if you want to write it at theta 1, you can write it as theta 1 dot E naught dot, which is same as this, because E1 and E naught are same. So z1 and z naught is same for this kind of, in for this case. And the magnitude of this velocity, that is angular velocity, will be nothing but theta 1 dot, which actually we require in this case. Similarly, V, that is the linear velocity of the center of mass, actually is equal to, if we talk about this point, so this is, since this is just rotating, but because of the length of this link, it will have a linear component. So that is L by 2. If we assume this is at L by 2, so L by 2 into theta 1 dot. So that is generally given by, if you write it in vector form, so this is in this frame x1, y1, z1. If we write the position of this point, the center of mass, so that will be L by 2 along x1. So we can write it as L by 2 I1. Alright, but because this is just the position, so for velocity we need the time rate of change of this part, so that will be, since L is constant, so it will be I1 dot. Alright, so we can say L by 2 I1 dot. I1 dot in mathematics, if we talk about these, the change in this vector, actually, because this is rotating like this, so this will be nothing but omega cross I1. It's a typical mathematical, can say, or maybe physical way of writing I1 dot is nothing but omega cross I1. So which will be given by L by 2. Omega is nothing but theta 1 dot E1. So theta 1 dot E1, fine, cross this I1. Alright, so this can be written as theta 1 dot is scalar, so theta 1 dot L by 2. So E1 cross I1. So E1 is out of the paper, cross I1. So this will be a cross product of E1 and I1, which will be nothing but a vector along, a unit vector along Y1. So it will be J1. So you can write it this way. So this is your linear velocity at the center of mass. So you can put this now, since J1 is in frame 1, so we can put it in frame 0 again by doing like this. So it will be theta 1 dot L by 2. So you need to have a rotation matrix from which transforms it from 1 to 0 of J1 and 1. Alright, so this is how we do it basically. So now this can be taken up like this. So we have R of 1 to 0 is nothing but rotation about z axis, so it will be cos 1 minus sine 1 cos 1 0 0 and 1 here. All right, so and j 1 and 1 is nothing but j vector. So this is 0 1 0. This is along y-axis, so it should be 0 1 0. So post multiplying this rotation matrix with this will give us, so we can say r1 0 j1 1 is equal to, this will be minus sine 1, this will be cos 1, and this will be 0. So v will be given by theta 1 dot L by 2 minus sine 1 cos 1 at 0. Or you can also write it as this way: theta 1 dot L sine 1 theta 1 dot divided by 2 L cos 1 divided by 2 and 0. So now this is the velocity vector, and obviously if you want to find out the magnitude of this velocity, that is magnitude of v, so which is required for the kinetic energy. So this will be nothing but the under root of theta 1 dot L theta 1 dot square L1 L square sine square theta divided by 4 plus theta 1 dot square L square cos square theta divided by 4 plus 0. So this will be nothing but, if you take this is all same, so sine square theta plus cos theta is nothing but 1. So this will come out of this. So you can even write the step theta 1 dot square L square by 4 sine square theta plus cos square theta. So this will be equal to under root of theta 1 dot square L square by 4, which is nothing but theta 1 dot L by 2. So your velocity is finally nothing but theta 1 dot L by 2. So this thing can be easily taken by intuition also, because velocity in this case, linear velocity will be nothing but theta 1 dot L1 L by 2, because that's what the arm length and the angular velocity. So this can be directly taken, but this was just to demonstrate how actually it follows the basic principle of transforming from frames and how we basically can get it easily. So we should be clear about these concepts. Now we can basically substitute these things in the expressions of kinetic energy here. So let's say T now will be equal to half m, and V is nothing but theta 1 dot L by 2. So half m is, you can just verify it, theta 1 dot L by 2. So plus half of I. So I is about center of mass. So we can write ml square by 12. This is I, moment of inertia about center of mass. And omega is nothing but, if you just see it here, omega is nothing but theta 1 dot omega square. Alright, so T becomes half m theta 1 dot square L square by 4 plus half of m L square theta 1 dot square by 12. So you can just add them because they are same. So m theta 1 dot square L square m theta 1 dot square L square by, this is 4 to the 8, this is 24. So we'll have 24 in the denominator. Alright, so this will be 8 3s are, so we'll have 3 plus 1 is 4. So we'll have 4 into m theta 1 dot square L square. So this means T is nothing but m theta 1 dot square L square by 6. Oh. Alright. So now we can add these potential energy and kinetic energies. So we'll have Lagrange is equal to T minus U So L will be equal to m theta 1 dot square L square by 6 minus what is u. Go back to the first page. So u was mgl sine theta by 2. So write mgl sine theta by 2. All right. So now this was our L. So now if we do the differentiation, first we'll have to now let's see back. What we have to do is we have to first find the variation of this L with respect to theta dot and with respect to theta, and then we have to differentiate again with respect to time. So we need terms like d dou L by dou theta dot. Okay, all right. So we have L now. Now we need to do dou L. We need we need dou L by dou theta dot, or you can say theta 1 dot, one and the same thing in this case. So it will be obviously differentiating with respect to theta 1 dot, so it's partial differentiation. So this will be 2m theta 1 dot L square by 6 minus, this will be 0 because there is no theta 1 dot. This is just a function of theta 1. This will be one of the parts. And we also require dou L by dou theta. So can again differentiate with respect to theta. So since theta 1 dot, so this is, we need just to differentiate with respect to theta. So this will be 0. And this part will have minus mgl sine of theta is cos of theta divided by 2. And then we need to differentiate with respect to time, d by dt of dou L by dou theta 1 dot. So this will be equal to, so we can just cancel this, 2 ones are 2 threes are. So ml square by 3 theta 1 double dot. Fine. So now the equation of motion becomes the equation of motion becomes as we see d by so it's nothing but d by dt of dou L by dou theta dot theta 1 dot minus dou L by dou theta is equal to tau. So substituting these things, so we have ml square by 3 theta 1 double dot minus plus mgl cos theta. We can write completely here, cos of theta by 2 is equal to tau. So now this is actually the equation of motion of the pendulum that you must have seen earlier also. We have done it in a elaborate way because this actually will help us to see complicated things like two link and three link manipulators, though we could have done this in a very simpler way also, by intuition or by maybe geometry also. By geometry we may do this very easily, but for two link and other complicated manipulators, geometry may not really be useful for us. That may complicate things further, but in this case geometry may have been very simple, and it may have just resulted in two-page answer to us. So now this is what our m is. So as if we represent this as this, m theta double dot plus h plus gamma is equal to tau. So in this case we have capital M is equal to ml square by 3. H is not here because we don't have centrifugal and Coriolis in a single link system. Those effects are not obviously there. We have gamma, which is the gravitational component, which is mgl cos theta by 2, and we have tau. All right. So the torque required to move the manipulator with some acceleration is given by this equation. So we can use this to control the manipulator. We can use this to control the one link system. All right. So in the case of two link and other higher degree of freedom manipulators, H will have a significant component. The Coriolis and the centrifugal components will come into picture. Gamma will be there, M will be there. So all this M terms will turn out to be matrix. Gamma will be a vector and H will be again a vector. So we'll have as the degree of freedom increases, the vectors or the matrices basically dimension increases. So in this case we have just scalar components because this is a single link manipulator. All right. Thank you.